First thing is we need to see if this is axial or torsional loads. It says there's axial force and axial force given, and we do not see any torsional force like this. So this question is about axial loads. Great. And number two is that if the question is asking if the object is going to fail, or is the object is going to be deformed, like, or what degree would it be deformed? So we can see that the question is giving us ultimate stresses, right? Which means it's going to ask us about the failure because we will probably have to get the stresses of each object, like set objects, and then we need to compare that with the ultimate stresses to see if it's bigger or smaller. If the stress of the object is bigger than the ultimate stress of the object, that means that the object is going to fail. So number three is that if the object, it's about the object. If the object is uniform or continuously varying or segmented. So we can tell that the object is not uniaxial because the definition of uniaxial is that the stress is not depending on the x and the cross-sectional geometry should not change. We can obviously see that the cross-sectional geometry from AB to BC is changing. As you can see, the cross-sectional geometry, the circle is getting bigger as it from the section of like cross-sectional geometry of BC is much smaller than the cross-sectional geometry of AB. And we cannot really say that this is continuously varying, even though the cross-sectional geometry did change. It's because continuously varying means that along the axis, the cross-sectional geometry is changing. Well, there is a change in the geometry. However, this is not continuously varying along the x-axis because there's a constant part. The cross-sectional geometry from BC is constant, and cross-sectional geometry from A to B is all constant. It's not dependent on the x-axis. It's not getting different. So it leaves us with the segmented, meaning that there will be a load between the two ends of the object, which we can see F1 and F2, and we will be having different free body diagrams along depending on where we cut the object, right? So that's question 4 of the analysis that we need to ask. And the last one we need to ask is if this is a forward reverse problem. This is a forward problem because it's asking us what's going to happen given the properties of material or the object. The reverse problem, by the way, will ask you, well, this is like a situation that happened. This failed, or this is elongated. So given this information, can you tell me about the material characteristics? That could be the reverse, but that's not the case for us. So we will be seeing what the outcome of given all these information. Would it fail or not? So this is a forward question. So let's solve this question together. So number 1 is that we need to draw a free body diagram. Because this is segmented object, we need to really be careful of like where we basically divide and segment our object. What I like to do is, because there's a very apparent like segment BC and AB, and we want to compare the stress of AB and stress of BC with all the ultimate stresses that we have to see if any segment is breaking, like failing or not. So if segment AB is failing, but segment BC is not, the object is still failing because segment AB is failing. So we will be solving for stress of AB and stress of BC and compare it with it. Which means we have segment BC and AB, and we need to get internal load. To get internal load, I'm going to slice it like right over here, and to get like NBC, and I'll slice it here so we can get the load of NAB. So let's draw the free body diagram given the information. The first part here and the second part is here. So first part is BC. So this is C, and there will be B somewhere along the lines of here. And we have internal load of BCX. And then we can see that there is axial load of force F2, which is, by the way, we are given. We know this value. To get the stress of BC, we know the stress equation is force over area. So we can say that it's this over area, the cross-sectional geometry of section BC, right? And this should be in pascals. So let's solve for this. Using the equilibrium equation, we know that the sum of all the forces in x-axis should be 0. And all the forces in the x-axis in this free body diagram is negative the internal load of section BC and force F2. And I put negative because we defined as a class in general that right is positive and left is negative, and they're all towards left, so I just put negative, which should be 0. We can rearrange this as NBCX is equal to negative F2. And negative F2 is negative 2200 newtons. And area of BC, by the way, is, because it's circle, it's definitely going to be pi r squared. But what is r? R is d2 over d. Because d2 is the diameter of the circle, r is d2 over 2. Yeah, d2 over 2. So we can write pi d2 over 2 squared, which will give us pi d2 squared over 4. And sigma BC would then give us force over area, right? Which is negative 2200 newtons over pi d2 squared over 4. So this, we can plug in d2, and d2, by the way, is 0.4 centimeters, and this is 0.004 meters, right? So we can plug that in, and we will get a value of negative 1.75 times 10 to the 8 Pascal. And because all the ultimate stresses in megapascal, I'm going to convert it into megapascal too, so it's easier to compare. And this is negative 1.75, no, I'm sorry, 175 megapascal. So we got that the sigma of BC is equal to negative 175 megapascal. Now, I'm gonna delete this. And let's see the different part, which is segment AB. So similarly, we are going to draw a free body diagram for AB, where we want to know the internal load of AB. We can write that by having F1 and F2 over here. And like we said, all the forces on x direction should be 0, which means negative NABX plus F1, negative F2 will be 0. So we can also rewrite this as F1 negative F2, which we know F1 and F2, it's going to be 1200 newtons. The area R is d1 over 2, therefore pi d1 2 squared is the cross-sectional geometry of section AB, which is pi, this is 0.01 meter, 0.01 meter over 2 squared. So stress of AB is going to be 1200 newtons over pi times 0.01 meter squared over 4, which, if you calculate this, will become 1.52 times 10 to the power of 7 pascals, and converted to megapascal, it's going to be 15.3 megapascal. So we have stress of AB as 15.3 megapascal. Great. So moving on to the next. Now that we have sigma BCAB, we want to actually now do a stress analysis, given that UTS, UCS, and USS. So in order to do this, by the way, we will be solving for a lot of a lot of things. Yes. So sigma max, what I like to do personally is to compare the objects like max and minimum and find and compare it with like the stresses, meaning that the stress max, if there's positive and negative, the stress of the max is going to be positive, and the positive stress is tensile stress. Mhm. And then, oh, sorry. Oh, where'd it go? Tensile stress. And sigma of minimum is often going to be negative, which is going to be compressive stress if there's positive and negative. So sigma max of this object would be 15.3 megapascal because it's a bigger number than negative number, right? So we will compare this with UTS. And sigma min is going to be negative 175 point 175 megapascal. And we will be we'll be comparing this with UCS because of compressive stress. Now we need to find shear. So in terms of shear, I want to compare max shear for segment AB and max shear for segment BC. So let's do AB and let's do BC. Because it's a uniaxial, we can write this as AB and over BC. And yeah, this is going to be sigma x over 2, and it's going to be sigma x over 2. So the shear stress of BC is going to be the stress of BC divided by 2, which is going to be negative Pascal over 2's absolute value, which we will get 87.5 megapascal. And for this one, for AB, it's going to be, which gives us 7.65 megapascal. So what's the max shear stress we see? So shear stress analysis. So for shear max, it's going to be 87.5 megapascal, which we will compare to USS. So UTS given is 18 megapascal. The max stress, so max tensile stress is smaller than ultimate tensile stress. So it won't fail in terms of tensile. The minimum is 175, but we're only comparing the magnitude of it, right? So we're comparing magnitude of the compressive stress. So this is going to be not failing. So far is 87 megapascal, and unfortunately, our object's shear stress is bigger than how much it can hold. Therefore, it's going to fail due to stress. So I hope this makes sense, and I hope